Hey guys, welcome back. Today we're going to talk about air masses and fronts. Now these are very important for you to know. All weather has to deal with fronts, right? So let's pay attention, let's really learn these. Okay, so here we go. So what is an air mass? An air mass is defined as a large body of air with very similar characteristics. Now, generally speaking, air masses are generally defined by temperature and dew points. These are called moisture parameters. Okay? Air masses are named based on the source region of the air mass itself. Now, I'm going to blow this up so you can see it better. There are different types of air masses. Now, we have continental polars are characterized by cold and dry air, and these originate closer to the poles over landlocked regions. Now, if you'll see up there in the middle of Canada, the CP, that stands for continental polar. Now, continental tropical are warm, dry, that's how they're defined by, and these originate closer to the tropics over landlocked regions. Okay? Now, maritime polar are cold and damp, and these originate closer to the poles over the waters. You can see the MP up there. Now, maritime tropical are warm and humid, and these originate closer to the tropics over water. Now, the Arctic or very cold originates in very cold landlocked areas such as up around Alaska. So how do we analyze air masses? Air masses, they're very easily identified by comparing it to other air masses. Air masses can be modified with time, most notably by days of sunshine or lack thereof. Fronts are the dividing lines between air masses, so understanding air masses means understanding where fronts are located. Now you need to remember that. Fronts are dividing lines between air masses. So what is a front? A front is a narrow transition zone or boundary between disparate synoptic scale air masses whose primarily discontinuity is density. It is synoptic scale along the length of the front, but mesoscale across the front itself. Now, these are commonly associated with moisture gradient, temperature gradient, wind shift, pressure troughs, and convergent boundaries. All right, so rules for finding a front. Look for a strong temperature gradient. The front is located on the warm side and is the sharpest gradient. Likewise, look for a strong dew point gradient. The front is located on the moist side of the sharpest gradient. Generally found in a pressure trough, look for 3-hour pressure changes. Fronts will show a decrease in pressure followed by a rapid increase in pressure after the frontal passage. Look for a sharp change in wind direction. A cyclonic shear in wind direction usually indicates a frontal passage. Check weather and cloud patterns that they are usually associated with for different kinds of front. We'll talk more later on this. But I want to cover something real quick. All right, so let me put this back up just for a second. Here it says gradient. What is a gradient? I want you to think very simplistically about you've got a point and you've got a point. Okay? Now, in between these 2 points is a distance. Okay? So in between 2 points, you've got a distance. Now, you heard it talk about temperature gradient. You heard it talk about dew point gradient. So what is it? A temperature or dew point gradient is just how much the temperature or dew point changes between this point and this point. That's all it is. Okay? So if you hear anybody, or especially me, say temperature gradient, it is a change in temperature or dew point over a given distance. That's it. A gradient is a change in temperature or dew point over a given distance. So don't stress yourself out too bad about these words. I'm going to try my best just to give you the simplistic definition of them. So that's all a gradient is. If it's a temperature gradient, it's a change in temperature over a given distance. If it's a dew point gradient, it's a change in dew point over a given distance, okay? So what kind of fronts do we have? You need to know all these types of fronts. I promise you, you're going to see these again, okay? A cold front. A cold front is noted by cold air advancing and displacing warmer air that exists. A warm front, noted by cold air retreating from an area. A stationary front, while differing air masses exist along the boundary, little movement is analyzed in the air masses. They just sit there, okay? An occluded front is a complicated process where the surface lobe becomes completely surrounded by cooler cold air. Occlusion processes can be of a cool type or a cold type. We'll talk about that more in just a bit, okay? So let's look at a cold front. Now, a cold front is marked on the map by a solid blue line with blue icicles or triangles hanging off of it. They remind me of icicles, okay? Now, the triangles point toward the warm air, all right? Now, the slopes of a cold front can be 1 over 50 or up to 1 over 150. Well, Shannon, what's a slope? Well, glad you asked. So these fronts have shapes, okay? And a lot of times, a cold front will be shaped something like that. All right. Now, you'll see it on like weather maps when you're watching the news at night or something like that, and it'll look like this, right? And then you'll see the little triangles coming off of it. That's what it'll look like on the weather maps. But that's not what it's talking about when it's talking about the slope. The slope is the shape of the wind and change. Okay? So the slope is just the shape of the cold air if it's a cold front, or the warm air if it's a warm front. Okay? Now the slope of a cold front could be either 1/50th or 1/150th. But try not to get too bent out of shape about the slopes and all that. All right, just know that each slope has, or each front has a slope, okay? Now these are associated with cumulus and cumulonimbus clouds ahead of the front in the warm air sector, producing showers and thunderstorms, okay? Here's a simple rendering of what I was just talking about, okay? So I'm gonna kind of step behind here, right? So if you will see right in this area here, I don't know if you can see that through the slide, but right in that area there, you can see that sloping action of the advancing cold air. That is the slope of this cold front, all right? Now out ahead of it, you'll have the showers and the thunderstorms in the warm air sector, okay? And as you can see down at the bottom, the line going across the boundary, that's the relative movement of the whole front, okay? But just know the slope is that slope that the cold front takes, or any front takes. So let me blow this up so you can see it. So this is normally how a cold front will interact with the warm air, right? So there over St. Louis, the front has already passed and the colder air has replaced the warmer air. Now the slope of the cold front is in between St. Louis and Indianapolis. Well, that is triggering showers and thunderstorms ahead of the cold front where you have the cumulonimbus cloud. Now, if you'll notice on out towards Columbus, Ohio and Pittsburgh, Pennsylvania, the clouds are starting to form. Well, if you go back to the three stages of a thunderstorm, well, Pittsburgh and Columbus are starting to see the towering cumulus stage of the thunderstorm, while Indianapolis is in the mature stage of the thunderstorm, and St. Louis has just got through with the dissipating stage of a thunderstorm. So this is an animation of a cold front. You see the slope there, and you see how the clouds are formed. The showers and thunderstorms start. As the cold air advances, the warm air is lifted, and therefore you have the cloud formation and the thunderstorm formation. So the cold front, so what do we need for our thunderstorm formation? Let's look at it. Well, we need an unstable atmosphere. We need a lifting action, right? So we've got the unstable atmosphere. That's the warm air out ahead of the cold front. Now we need a lifting action, right? So here comes that cold front. That cold front is sloped down, and as it moves forward, it forces that warm air up. The warm air condenses, goes through the three stages of a thunderstorm, the towering cumulus, the mature, the dissipating, and that's how you tie all of these things together, okay? So let's talk about a warm front. So a warm front is marked by a red line on the map with semicircles pointed towards the cool air, okay, in the direction the warm air is retreating to. Now these slopes range from 1/100th to 1/300th, generally associated with stratus-type clouds, overcast skies, fog, and general rain or snow. Now let me blow this one up so you can see it. So the advancing warm air behind the front, the little red circles point towards where the cold air is, right? Now as it moves, the warm air rides up over the top of the cold air. Cloud develops again because of frontal lifting of the warm, moist air. All right, cold air is denser than warm air, so the warm air will go over the top of the cold air. And that's what this is showing you, right? So you got a warm front that's moving towards Pittsburgh. It's over west of St. Louis. And as it goes over St. Louis, you get nimbostratus clouds built, and then it transferred into altostratus, cirrostratus, and cirrus on out towards Pittsburgh, Pennsylvania. But eventually, as that warm front moves forward, those stages and clouds will move over Indianapolis, Columbus, Pittsburgh, and so forth and so on down the line. Now here is the animation of a warm front. So you got the warm air going up over the slope of the front. The clouds are built, and therefore the rain and showers persist. Okay. Now a stationary front. Stationary front is marked by alternating blue lines and blue triangles with red semicircles, pointed in the direction of the warmer air. The red lines and red semicircles point in the direction of the cooler air. Now, this is usually noted as a quasi-stationary, as it is rarely ever completely stationary. It will drift back and forth just a bit, okay? Now, occluded front. Now this is marked by a purple line with alternating purple triangles and purple semicircles, all pointing toward the direction of the frontal movement. Now if you see an occluded front, and whichever way the triangles and circles are facing, that's the way the front is moving, okay? There are two general types of occlusions, cool type and cold type. You're going to need the password fronts for this quiz, all in lowercase, and I will give you that reminder at the end of our presentation today. All right, so let me blow this up. So here's the 3D idea of an occluded front. You got advancing very cold air behind an occluded front. Now, the direction of frontal movement is noted by the triangles and semicircles pointing to the right. The receding cold air ahead of the occluded front, and then in between, cloud development because of frontal lifting of the warm, moist air. Okay? So here is an occluded front depiction. So you got cold air, and then you got warm air up above. And so that occlusion is up above the cold air there, and as that thing moves forward, the frontal lifting occurs, and then you get your showers and storms. So let's talk about cyclones, and let's start putting this all together, okay? So there's two types of cyclones. There's tropical, which is a warm core, and extratropical, which is a cold core. Extratropical cyclones are characterized by having different air masses, frontal movements, where tropical cyclones do not. We will concern ourselves with the extratropical cyclones in this presentation, okay? So typically, cyclones are represented by using the Norwegian cyclone model. It's simplistic, but a good way to start understanding the surface lows and cyclones. Now, you guys must understand the four-dimensional view of a cyclone. You got north-south, east-west, up-down, and time. All right, I'm going to blow this up. So the cyclone, as you can see here, we got a low-pressure system. We got a cold front that extends off the lower portion on the left here of the low-pressure system, and a warm front coming off to or parallel to the low pressure system with warm moist air out ahead of the cold front. Now, on the right hand depiction, you see that the low is there, but now those fronts have occluded. Now you got a cold air mass, you've got a warm front out ahead of the cold front, and now you've got a small convergence area in between the cold and the warm air. Now, 9 times out of 10, when you see this setup right here, you're going to have some very nasty, very violent thunderstorms, okay? So, the Norwegian model, step 1, you got a subtle boundary that exists, okay? Now, step 2, a wave forms on that boundary. Step 3, the cyclone becomes mature. Step 4, the occlusion process happens. Step 5, cold air dominates near the end of the cyclone process. All right, so here is a satellite version of a cyclone. Now, you can see the approximate locations of the fronts here by the movement of the clouds on the satellite, and general features of an occluded low pressure system or a cyclone. So you see the dry inclusion there, all the way from Middle Missouri up into the upper peninsula of Michigan and into Canada there. You see all the stratus-type clouds, and then you see the showers along the cold front down through Tennessee and the lower parts of Arkansas, and then Mississippi there. And then you see the occlusion up top indicated in the purple. Here's the radar view of what that cyclone looked like. And you can see all the moisture on the right-hand side there. That is the moisture of that cyclone, and then the rain that is involved with that cyclone. There's your occlusion, your warm front, and your cold front. Now, the cold front, if you'll notice, is noted by that line, that linear line of thunderstorms there on the left-hand view. Now, a cyclone center just south of Wichita, Kansas, fronts developed. Now, this is a weather product that you will be able to look at on ForeFlight and weather 1-800-Weather Brief and stuff like that. But this shows wind movements, temperatures, and things of that nature. Now, here's the cyclone 6 hours later, and it's located near Kansas City, Missouri. So I'm going to flop this over. So Kansas City, Missouri is located like right in here, okay? So if you blow that back up, you can see that L just north of Arkansas there, where the greens and blues and yellows start to converge, all right? That is the low pressure center, okay? Now this is now a mature cyclone with developed fronts, okay? And it's going to show you all these things better here in just a second. Now another 6 hours, the cyclone or the low pressure system is beginning to occlude, and the surface low is being surrounded by the colder air. Another 6 hours into the future, it's now fully occluded. The surface low is completely within the cold air mass. Another 6 hours, the cold front has surged well east while the center of the cyclone has remained over the Midwest. Now this is an animation showing you exactly what it was talking about, all right? So you can see that it starts out over Wichita, Kansas, and then it finally gets occluded and ends up in Wisconsin, the low does, while the main part of the storm is wrapping all the way from Michigan down into the Gulf of Mexico. So let's review on how to find fronts, all right? So number one was to look for a strong temperature gradient. Now remember, a gradient is nothing more than a change in temperature over a given distance, right? So do you see one there? I know it's kind of hard to see, but it's going to show you here in just a second. So these are all the winds associated with the fronts. Now note, this image, the dashed blue lines represent pressure rises while the solid blue lines represent pressure falls, okay? The numbers represent millibars per 3 hours of rise or fall. The yellow vectors point in the direction the wind is blowing, okay? Let's see, I think I might have went too far. Yep. All right, so the last rule is to check cloud and weather patterns, all right? So if you can see on the left, you see that band of showers and thunderstorms, that is a front, okay? So every cyclone presents unique characteristics. While the satellite and radar did not show the front very well, the temperature, wind, and moisture analysis provided a clear-cut picture where the front should be analyzed. The rules for finding fronts should not imply that all rules need to be met. It means that you need to use all of those tools to find the front. Often, fronts are very subtle, and just one rule may not be useful, okay? Now this is a sounding. You know, last week we talked about a sounding, so we know that that's where the National Weather Service just sends up a weather balloon and it takes different readings throughout the atmosphere. Well, this is what it looks like graphed out. Now from the same data as the previous image, this sounding is from Omaha at 6 p.m. The sounding shows well the slope of the cold front. Now notice that the cold air has settled in very well from the surface to around the 800 millibar height and altitude, and you'll notice that the wind shift that goes along with that altitude. Now, I don't expect you to, you know, really dissect this very much, but I just wanted to show you that even though you might not be able to pick it out very well, but if you use, you know, just by using one product, if you use all the products available to you, you can pick out where the fronts are located, all right? All right, so from the same data set, this one was taken from around Lincoln, Illinois, okay? So you can see all the different changes that this front is going through, this cyclone is going through, okay? And here's a cross-section of that same information that we were just looking at. And then here is just the precipitation and thicks. It shows wind and the precipitation that was included with that front. Now see, here's the slope of the front. Now, just looking at this map, you can tell by temperatures where the front's located. So if you'll notice, like down in the Gulf of Mexico, Texas, you got your deep oranges, your deep reds, and then it transitions into yellows and greens. And then when the cold front hit, it goes to blues. So if you look at a map with temperature colors on the map, you can tell where the front's located. Just look for where it goes, changes from yellow to green to blues, okay? Now temperatures at the 850 millibar height, about 1,400 meters above the surface, with frontal features overlaid. Now notice that the cold front is a little further west and the warm front is a little further north. The low is a little further northwest as well. You can tell by the marked difference in the change of colors there, okay? Now all these is going to do is just show you the same depiction at different levels, okay? So guys, fronts they're fronts. I mean, you got cold front, warm front, occluded front, and stationary front. Just know that a cold front is advancing cold air that's going to replace warm air, all right? A warm front is warm air that is advancing and replacing cold air. An occluded front is where a warm front and a cold front meet up, and the warm front occludes up over the cold front, okay? And a stationary front is a front that has very little to no movement, all right? All right, guys, well, that's all for this one. So what I want you to do is remember that for your password for this quiz, it's front, all lowercase, and to have all of your assignments done by 11:59 p.m. tonight. I hope you guys have a great week, and we will see you around. Blue skies.